Well, hello, welcome again to our journey into algebra and number theory, and in this section we're going to look at the Gaussian integers and questions involving sums of squares. So our aim in this chapter is to examine which numbers can be written as the sum of two squares. For example, you quickly reveal by trial and error that you can't write 7 as the sum of two squares, while if you take 26, which is very easy, you can write that as 5 squared plus 1 squared. The approach we're going to use here is to examine a very special ring, and that's the ring of so-called Gaussian integers, whose properties are remarkably similar to the integers. It's an integer multiple of the complex number I, where I squared is minus 1. So we're going to write that as a z square brackets I to mean the set of all things of the form a plus bi, where a and b are integers. And these are called, this is the ring of Gaussian integers. Firstly, observe it is a ring. You can add, subtract, you can multiply and stay inside the set, but not divide in general. So for example, we can take two Gaussian integers. Here's one here, 3 plus I, and I can add minus 5 plus 2i, I get another Gaussian integer, or I can multiply these out using our usual rules of multiplication, which gives me minus 17 plus I. You will have come across complex multiplication in earlier courses in mathematics. We'd like some notion of absolute value in Zi. We'd like to be able to measure the size in some sense so that we can find an analogue of the division algorithm. Now it's convenient to use the square of the modulus of the complex number. That is, if we take a complex number alpha is a plus ib in this ring Zi, I define the norm of alpha, which I write as n of alpha, to be alpha times alpha bar, and that's just alpha squared plus beta squared. Another way of writing that, you could also write this, of course, as the modulus of alpha all squared. Now, it's a nice little exercise to show, it doesn't take much effort to show that this norm is multiplicative, that the norm of alpha times beta is the norm of alpha times the norm of beta for any alpha and beta in Zi. This, in fact, is a very nice observation, because we'll see we can use this one. It has a nice connection with sums of squares. So the proof of this is just a simple exercise in algebra. Now observe that an integer is the sum of two squares if and only if it is the norm of some Gaussian integer. Well, that's very nice, because it gives us a connection now between sums of squares and norms. And if n1 and n2 are both the sum of two squares, then so is their product. For example, if we take 5 is the sum of two squares, because it's just 2 squared plus 1 squared. And we can write that as the norm of 2 plus I. Now, of course, this is not unique. I could have written this as the norm of minus 2 plus I, or minus 2 minus I, or I could have written this as the norm of I plus 2, or plus or minus, and so on. Lots of different choices here. So I'm going to take 13 as the sum of two squares. It's 3 squared plus 2 squared. And I'm going to write that as the norm of 3 plus 2i. Again, there are lots of choices here. So when I multiply 3 times 5 to get 5 times 13 to get 65, then by using our little theorem here, that's the same as the product of these norms, which is the same as the norm of the products. And you multiply these two together, you get 4 plus 7i. Now if you take the norm of that, that's 4 squared plus 7 squared. And that means I can write 65 as the sum of two squares as 4 squared plus 7 squared. Now, as I mentioned here, we could also have written 5 as the norm of 2 minus I. And if we multiply that out, we get the norm of 8 plus I. So I could also have written 65 as the sum of two squares in a different way. Now, as I mentioned, there's lots of other possibilities, but I'll leave you to check that the other possibilities do not give any new sums of squares, except to have it in the opposite order, or perhaps to have it as minus 8 squared plus minus 1 squared or something. but essentially there are no other essentially distinct ways of writing 65 as a sum of two squares. Well, we'd like to say which elements of this have multiplicative inverses. We know that not every integer, not every Gaussian integer has a multiplicative inverse, but some do and some don't. Clearly 1 and minus 1 do, and so do I and minus I, because 1 over I is just minus I when you realise the denominator in this. Now it turns out that these are in fact the only such elements. That is, the numbers that correspond to the number 1, or possibly minus 1, in the integers turn out to be just plus or minus 1 and plus or minus I. Second theorem enables us to check which elements have got multiplicative inverses. So if alpha is in Zi, the following are equivalent. Alpha is a unit, that is an element which has a multiplicative inverse. Its norm is 1, and the only units are plus or minus 1, plus or minus I. Well, 3 implies a 1 is trivial. It's really that's obvious. So if alpha is a unit then, so we're going to suppose 1, if alpha is a unit, then there exists a beta in Zi such that I can multiply alpha times beta to get 1. Use the properties of the norms, take the norm of the product is the product of the norms, and that's the norm of 1. Now the norm of 1 is 1, so that tells me that the norm of alpha is the norm of beta, which equals 1, because the only positive divisor of 1 is 1, and that tells me that 1 implies 2. And finally, if the norm of alpha is 1, then with alpha as a plus ib, then the norm of this is alpha squared plus beta squared is 1, and that clearly we're back in the integers, and the only solutions of this is alpha's plus or minus 1, beta, b is 0, or a is 0 and b is plus or minus 1, giving us the 4 units, and so 2 implies 3. Well, what can we say about primes? Can we extend the notion of primes to the set of Gaussian integers? For example, should we regard 13 as being a prime in this set? Well, it is a prime in the integers, but probably not here, because I can factorise 13 as 3 plus 2i and 3 minus 2i, and so I really would not expect what I'm going to call a prime to factor. On the other hand, by trial and error, we find that the only possible factors of 7 in the Gaussian integers are plus or minus 1, plus or minus I. Well, of course 7 goes with this as well, and these are units. And the factorisation 7 equals 7i times minus I is not a very convincing factorisation. One might compare trying to factor 5 as 1 times 5. So the following then seems to be a sensible attempt at defining a prime in Zi. So we take a number. We're going to use Greek letters here. This is not the number pi, 3.14159. This is just a symbol for a Gaussian prime. So we take pi in Zi as a Gaussian prime if and only if, whenever you have any sort of factorisation in the Gaussian integers, then one of these two has to be a unit. And that's going to be our definition of prime in the Gaussian integers. So 7 is a prime, and so is 1 plus I turns out to be a prime, which we can't quite see yet, but we'll see a way of classifying the primes shortly. So we're going to see later how to check which complex numbers are in fact Gaussian primes, but firstly we're going to try and get an analogue to the division algorithm. Now recall that in the ordinary integers, given integers a and b, we can divide one by the other. We can write a as bq plus r, where this r, the remainder, is bigger or equal to 0, but less than what we're dividing by. Now there's no ordering in the complex numbers, no simple ordering, so in replacing the inequality sign, we're going to do that using the norm. So I'm going to, here's our theorem. This is the the equivalent of the division algorithm in the Gaussian integers. So we take two Gaussian integers, then the theorem says there exists a Q and R Gaussian integers so that you can divide beta by alpha goes Q times, and you have a remainder R where the norm of R is bigger or equal to naught but less or equal to the norm of what you're dividing by. Now, before giving the proof, an example of how it works might be useful here. So here's beta is 3 plus 2i, alpha is 1 plus I. So I'm going to divide one by the other. I'd get this. You realise the denominator, so you multiply top and bottom by 1 minus I, and simplify gives you 5 minus I on 2. And now you divide this through, you get 2.5 minus a half I. And I'm going to take the integer part of this, or the nearest integers, so I'm going to write this as 2 plus a half, and minus a half I I'm going to write as minus I plus a half I. Now, by the way, this is not unique, because I could have written this as 2 plus a half minus a half I. And I get a different Q and R. So the Q and R are not unique anymore in this scenario. Now we put R then, we take that as beta minus the integer part, this 2 minus I times alpha, and we simplify that and it turns out to be I. And that means then I can do a division on these two, my beta and my alpha. So I divide this by that, it goes 2 minus I times and a remainder of I. So there's the Q, there's the R. And the norm of R is the norm of I, which is 1, which is less than the norm of what I was dividing by, which is 2. Now, a good thing to do is to sit down and practice doing some of these divisions and till you get the hang of the idea of this. Now, here is the proof of our theorem. So we write beta on alpha is x plus iy, where now x and y in general will be rational numbers. Now we want to get back into the integers, so I choose s and t so that x minus s is less than a half. So x is a rational number, and I take the nearest integer to that one, or perhaps an integer, so that the difference is less than a half, and I do the same with y and t. Which is roughly what we did here. We split up the 2.5 into 2, and then we said, well, there's a half left over. So the difference was less or equal to a half, and we did the same up here with the y and t. And now we let q then to be s plus it, so q is a Gaussian integer. And we put r to be which is going to be our remainder. We simply take beta minus alpha q. And so that means r then is a Gaussian integer, and we have the division. So beta is alpha q plus r. Now what we need to do now is just to check that the norm of r is less than the norm of alpha. So the norm of r is the norm of beta minus alpha q. I can factor alpha out of this, so I get the norm of alpha, beta on alpha minus q. Now the norm carries across, and so this is the norm of alpha times the norm of beta minus, so this is the norm of r, beta on alpha minus q. So this is the norm of alpha. Now this one here is x minus s all squared plus y minus t all squared. And now we set it up so that this difference is less than a half, and so this is less or equal to the norm of alpha times a quarter, a half squared plus a half squared. It's a quarter plus a quarter, which is a half, and that's less than the norm of alpha. Now, as an example of this, here are two Gaussian integers. We'll do another example of the division here. So I take beta over alpha, so I get that divided by this number on 2 plus alpha. realise the denominator, so multiply top and bottom by 2 minus I. Simplify gives me 7 minus 11I on 5. And that's 1 and 2 fifths minus 2 and a fifth I. So we take the nearest integer to this one, which is probably 1, and then I've got a fifth left over, and I take the nearest integer here, which is minus 2, and I've got another fifth left over. And finally I take the remainder then by taking 5 minus 3I minus the 1 minus 2I, which is what I got here, times the thing I'm dividing by, the alpha. When you simplify all that, you get 1, and there's the division algorithm done. Now the notions of ideal and principal ideals, which led us to GCDs, carry across nicely. So in particular, we're going to make the following definition. If alpha and beta are Gaussian integers, then we can't use the anymore. It's greatest common divisor because it's not unique. So greatest common divisor of alpha and beta is the Gaussian integer gamma, or is a Gaussian integer gamma, so that gamma divides alpha, gamma divides beta, and if delta is any other common divisor, then delta is a factor of gamma. To evaluate the GCD, we simply modify Euclid's algorithm slightly using our new division algorithm. So for example, to find a GCD of these two numbers, we divide, and we've already done that a minute ago, and we saw that 3 plus 2I is 1 plus I over 2 times 2 minus I plus I, and that means a GCD of these two has to also go into I, so this GCD is equal to the GCD of 2 minus I and I, but then this one, when I divide this by this, it goes into it that many times with no remainder, so there's no more, this is the last non-zero remainder, so a GCD is 3 plus 2I, I is a GCD of these two numbers. Now, as in the standard Euclidean algorithm, the GCD is the last non-zero remainder. So observe then that 1, minus 1 and minus I are also greatest common divisors of these two. Thus, the GCD is unique, well, up to multiplication by a unit. So you might recall that in the integers, the units are plus or minus 1. We defined the GCD to be positive to avoid non-uniqueness. We can't do that here because in the complex numbers you don't have ordering, so you can't say that minus I is negative or something. It doesn't make sense. Now the relationship carries across between GCDs and ideals, also carries across here. For example, if we consider this set S, which is all the Gaussian integer linear combinations of these two, then S is easy to show this as an ideal, and we'll see shortly that it's a principal ideal with generator I, because that was a GCD of these two. In other words, we can say that this S then is generated by I, but then it's easy to see that that gives you all of the Gaussian integers. So as in the case of the integers, we have the following important result, which we'll continue on in the next recording.